Fundamental and derived quantities. We have another categorization for quantities. Some quantities are fundamental or basic, some are derived. The physical quantities are derived into two categories: fundamental or basic quantities and derived quantities. Fundamental quantities are length, meter, the unit is meter, the unit is written inside the parentheses. Mass, kilogram, time, seconds. These three make the mechanics branch of the physics. Electric current, ampere, temperature, Kelvin, amount of substance, mole, luminous intensity, candela. All other quantities are derived quantities. So whatever quantity you can think of, for example, density, work, power, area, volume, whatever quantity other than these are derived quantities. So a list of basic quantities are written in this table again, and we see some examples here. These are independent quantities. All other quantities are based on them. Okay, let's see some example. Example of length. Height of a student is 1.5 meter. Example of mass. The weight of a book, it's better to say mass of a book. Let me make it like this. Mass of a book, because there is a difference between mass and weight. Mass of a book is half kilogram. Time. Duration of a race is 10 seconds. Room temperature is 293 Kelvin. The unit of temperature in SI units is Kelvin. Okay. Electric current, ampere. Current in a circuit is an example of it. Luminous intensity, brightness of a light source, is measured with candela. Amount of substance with a unit of mole is used in chemistry. Number of atoms or molecules is an example of this. Let's see some derived quantities. Area, these come from the combining basic quantities using formula. For example, area is length times width, so a unit is square meter. So two length dimensions are multiplied by each other to form this quantity. Volume is length times width times height. Of course, this is the formula for volume of a rectangular prism. So as you see, one length is multiplied by another length and multiplied by another length. So length is multiplied 3 times by itself to form this quantity. The unit is cubic meter. Speed is distance over time, so unit is meter per second. Density is mass over volume. The 1 unit of it, or SI unit, is kilogram per cubic meter. Force is mass times acceleration. The unit is Newton. It is also written with respect to base units, because we have some base units: kilogram, meter, second. These are units of basic quantities. So Newton is not a fundamental. Force is not a fundamental quantity. Therefore, its units is written based on units, based on basic units. So pressure is force divided by area. The unit of pressure is Pascal in SI. Pascal is equal to Newton per square meter. Energy is another derived quantity. It is calculated by force times distance. The unit is joule, and joule is equal to Newton times meter. Okay. In this example, we want to determine if these quantities are basic or derived quantities. So we know that work is a derived quantity. Work is a derived quantity. Length is a basic quantity. Power is a derived quantity. We know 7 basic quantities: length, mass, time, amount of matter, luminous intensity, temperature, and electric current. So by knowing these, we can determine if it's a basic quantity or derived quantity. Time is a basic quantity. Velocity is a derived quantity. Acceleration is a derived quantity. Okay. Base units and derived units. Base units are standard units around which the system itself is designed. For example, kilogram, meter, second. Derived units, as the name implies, are created by associating base units with each other. For example, the Newton, a unit of force, is derived from kilogram, meter, and seconds. How? Based on this formula, because we know that force is equal to mass times acceleration. Acceleration is equal to change in velocity over time, and velocity is equal to distance over time. Therefore, velocity, the unit of velocity is meter per second. So applying here, going back one step, meter per second divided by second. So the unit of acceleration is meter per square second. Going back one more step, force is equal to mass times acceleration. Therefore, the unit of force, which is Newton, is equal to kilogram times meter per square second. So this way we can say that 1 Newton is 1 kilogram meter per square second. All the units are SI units. Okay. Use the following formula to state the unit of work, power, in terms of kilogram, meter and second. As I told you, kilogram, meter, and seconds are base units in mechanics. So we can make all other units in mechanics for example, unit of work, which is joule, or unit of power, which is what in terms of these base units. So force is equal to mass times acceleration. We talked about it. Acceleration is change in velocity over time. Okay, we talked about it. Work is force times distance. And power is the rate at which work is done or energy is consumed. Energy over time or work over time, it is the same thing. Because work and energy have the same units. So we learned that unit of acceleration is meter per square second, and we learned that unit of force, which is Newton, is kilogram meter per square second. So let's apply it here. The unit of work is joule. Joule is force, so kilogram meter per square second times distance, which is meter. So it will be kilogram meter squared over second squared. And then the last one, power, is work over time. So the unit of work is joule. The unit of power is watts in SI. Watt is this unit divided by time. So 1 second goes to the denominator here. Kilogram meter squared over second cubed. This will be watts. So this is a derived unit, and it's written based on base units.